Hello, everyone. So, uh, we just had the quiz last time you were here. And so if you weren't here, then obviously you need to make up that quiz. And I needed to talk about a few things today that are a little different than what we had been dealing with. But remember, up to this point, hold on, let me see if I can. Okay, so this is the stuff that we had been working on. Oh my gosh, what is this doing here? Someone asked when they came over from Germany, they changed the spelling of my name, um, my family's last name. This is one of the ones I had seen before. Anyway, I'm not sure why that's still there. So we had looked at several different position time graphs, and then we had sketched motion maps based on those. We had talked about these three things here as being the details that you need to be able to recognize from a position time graph. You need to be able to tell, where does it start? Where does the object begin its motion on a position time graph? And you're supposed to know that that is called the y-intercept. That's how we know. We look over here at the graph and we see the y-intercept, and that is what tells us where the starting position is. Then we looked at the direction of travel, and how do we know that? Well, and we said whether it's tipped up or down on the graph, which way the line is tipped tells us which direction the travel is. And then we looked at, well, how fast or slow is it? Well, that's how much the line is tipped. The actual value or steepness of the slope tells us how fast. So those are the three things we really, really, really need to be able to figure out by looking at a position time graph, and then be able to articulate that both in words and in motion maps. So that was the goal. And again, so we went through these problems. And again, this is all in the previous video. So remember, we did all of this before. So I kind of changed gears. Now, I will bring up something though here to remind you that, like in this case, 40 meters, we said, was how far the person actually went. How much their position changed was 40 meters, because they were traveling at 5 meters every second. 5 meters every second for 8 seconds, that's 40 meters total, right? 5, 10, 15, 20, 25, 30, 35, 40. So 8 seconds worth of 5 meters every second gives you 40 meters of position change. But that's not where they were. Where they were is how far they went plus where they started. And in this case, because they started in a negative position, okay, below the zero on the position time graph, started in a negative position. When you add that negative, of course, then it tells you that they were only at a position of 38 meters, even though they went 40. So again, with this equation here that we wrote, the first part tells us the how far they went. We have to add to that where they started, and that total tells you where they currently are. So keep that in mind. Now, today then, I kind of started off with this. That has a name. What we're talking about, how far something goes or how much its position changes, that has a name. And it's actually called displacement. Oh, now I'm in the way. It's called displacement, okay? Displacement is the change in position. So remember, delta x is the symbol we used. Change in position is what we call it. That's like direct translation. Delta means change. X is the position. So change in position. And that is called displacement. So if you were to write out a definition for displacement, I would actually call it the change in position. That's it. Now, how do you find that? Well, mathematically, here's how this works. Okay, I want you to think through this. Oh boy, I'm not in a good place. I'm not in a good place. So this is how this works. The delta x, or the change in position, is where you ended minus where you started. Where you ended minus where you started. Now, final position. That's what the XF here symbol is, the final position. That's your position at the end. If you take away from that where you started, then you figure out, oh, that's how much my position changed. It's my final, where I ended, minus where I started. End minus start. Final minus initial. Okay? Now, let's go back to those graphs that we were just looking at. If I can locate them right here. Now, I kind of wrote this stuff out here. So hopefully, oh my gosh, let me get myself up here. If we look at the first problem that we did, and you had this written out, at least you were supposed to, we had said that the 56 meters is how far the person went. Because if you're going 7 meters every second, for 8 seconds, that's 7 plus 7 plus 7 plus 7 plus 7, 8 times, right? So 8 times 7 tells you that that person, that runner, ran 56 meters. That's not where the runner was, though. Because since the runner started at 4 meters a position, the runner is actually how far they went plus where they started, which means they are at a position of 60 meters at the end. That is the position after the 8 seconds has gone by, and that would be the XF, or the final position. Final position is 60 meters. Initial position, that is the y-intercept, that is the starting location, starting position, and that was 4 meters. So if you were at 4 meters at the start and you ended at 60 meters, then what this says down here, right, the final where you ended minus where you started tells you that you went 56 meters. You traveled 56 meters because you started at 4, you ended at 60. The difference there is your delta X, or change in position. So we're just kind of putting some names for to each of these pieces that we've been dealing with. And then down here, the last one, same thing. This is how far the runner went. This is where the runner started. That's the initial position. This is where the runner ended up. 38 meters is where the final position was of the runner. And so if you take, again, final minus the initial, and again, I put these, oh gosh, let's see. Oh no. Oh, I put those plus, I made them pluses because it's 38 minus a negative 2. It's 38 minus where you started, which was a negative 2. And when you subtract a negative, remember, that's the same as adding a positive, right? So that's why I made the minus signs pluses, because it's a double negative, and that makes it plus. So 38 meters minus negative 2 is actually 40 meters. So again, it's still correct. It's telling us when you take where you ended minus where you started, it is how far you went. That's how much your displacement was. So that's that. Okay, everybody got that? Hopefully, maybe. Hopefully I didn't confuse you too much. Now, that is different than this other term I'm going to bring up here. This other term that I'm going to mention is called distance. It is not the same as displacement, although many people use the two terms interchangeably. Let me get myself off the side here. So many people use those two terms interchangeably, that distance is the same thing as displacement. And several of you were trying to use the term distance on your graph for the tumble buggy, or we kept talking about distance for the tumble buggy. But that's not actually what we were looking at. We were looking at position, the actual location, where it is at specific times. Okay, not how far it went, We were looking at where is it at this time. That's position, not distance. Okay. And displacement is also not the same thing as distance. Displacement is where you ended minus where you started. Distance is altogether different. So, and this is what I did in class. Let me get myself, I don't like being off to the side there. In class, what I did was I stood on one of the squares, one of the tiles in the room, and I walked so many tiles off to the side. And I displaced myself by so many squares. And so I started at one blue square, and then I walked over 8 squares. So I displaced myself 8 squares. And the distance I traveled was 8 squares. So my distance and my displacement were the same. I started at position 0, which was a blue square right in the front of the room. And then I walked 8 squares over in the positive direction, which was a positive displacement of 8 squares, and the distance I traveled was 8 squares. Well, then if I walk back to the 0 position, the same blue square I started on, if I started on the 0 position blue square and I ended on that blue square, then how much was I displaced? 0. My displacement from beginning at the blue square, walking over 8 squares, walking back 8 squares, and I ended at the blue square, then my displacement is nothing. I did not displace myself. Yes, I was displaced for a moment, and then I came back to where I started. If I ended where I started, then I'm not displaced anymore. But did I travel a distance? Yes. What was the distance that I traveled? Well, if I walked 8 squares in the positive direction, then I turned around and I came 8 squares back in the negative direction, then how far did I go? My distance that I traveled was 16 squares. But my position is the same as it was when I started, so I'm not displaced from where I started. See, that's the difference between displacement and distance, and I hope that makes some sense. The distance is the actual length of the path you traveled. So if you double back on the path you traveled, then that counts for distance. That's how many steps or how many meters you actually went there and back. That's distance. Displacement just wants to know, where were you when you started? Where are you now? And how far away is that? That's displacement. Okay? It only cares about the 2 places, starting and ending. Distance wants to know, where exactly did you go the whole time? How many places were you? How many steps did you take? And then get back to where you are. It's the actual length of the path. I hope that makes sense. It's different. It's not the same. It can be the same value, but it isn't always. And it depends on, if you start changing your direction that you're going, then your distance is going to be different than your displacement. As long as you just stay going in one direction the whole time, then your displacement and your distance will probably be the same. But as soon as you start changing directions, then your distance is going to start adding up, but your displacement is going to be different. I hope that makes sense. Now, here's what we did after that. Let me get this thing out of the way. So I presented some scenarios here, and I described this thing called a velocity time graph. Okay. We've been talking about position time graphs. I think I need to make myself smaller. We've been talking about position time graphs. We've been talking about motion maps, and it almost doesn't fit. And I introduced this thing called a velocity time graph. Okay. Now, what we did was this. I had a tumble buggy set up at a 0 position. It went in the positive direction. uh, at a constant velocity. Now remember, I wrote these three things down because these are the three things that you're supposed to be able to tell from a velocity or from a position time graph. You're supposed to be able to identify these three things. Where did it start, the object that is? What direction is the object going? And what do you know about its velocity? Those are the three things that we need to make sure we understand and we can identify. So if you see a tumble buggy that's starting at the zero position, traveling at a constant velocity in the positive direction, what does that look like on an XT graph? So it would be good if you sketch all this right now. So pause if you need to, sketch all of this out. And then I'm going to kind of go through what we saw in class. So do all that and then come back. So here's what we said. Oh, come on. Oh, no. Am I not? Okay. Oh, let's go with the blue, I guess. Thin line. All right. So constant positive velocity starting at the zero position. Well, to me, that looks like this. So that looks like a positive slope, constant starting at the origin on the XT graph. That's what that looks like to me. Okay. Well, that right there. And that's what we see on the graph. That's what we've been seeing. Now, what does that look like for a motion map? Well, where did the tumble buggy start? Where did the line start on the actual graph? The starting position was at the zero position. And so again, for my motion map, it would be a dot like this. And then I would have arrows all the same length in the positive direction, indicating that that was a constant positive velocity for the tumble buggy. And then there's this thing called a velocity time graph. And this is a new thing. Now, if the velocity is the vertical axis now, and zero is at the origin here, that'd be zero velocity, not moving at all. Positive velocity is up here. Negative velocity is down here. Then what does a constant positive velocity look like on this graph? Constant positive. The velocity is not changing values, and it's positive. I hope your brain is engaged and you're thinking about what that should look like. It should look like this. Because again, the line is at some value. Again, we don't know what the number is, but since this is a constant slope, that means it's a constant velocity, which means it can't change values. The velocity value does not change. So whatever this value is here, and again, we don't have actual numbers, but it's positive because it's above the zero. That's positive, and it's not getting bigger or smaller. See, if it looked like this, that would mean that your velocity is doing what? It's getting bigger, right? And if it looked like this, you would say that your velocity is what? Well, those values are getting smaller. But that's not happening. The velocity is staying the same. And again, how do we know by looking at the graph? Because we're looking at the actual slope. Remember, the slope of this graph is the velocity. It is the velocity, and it is a horizontal line on this case, on this graph, because the velocity is a positive value and it's not going up or down. It's not going up or down, it's staying constant. So this was the first scenario we looked at. Then we put the tumble buggy on the track, ran the tumble buggy, and it showed us Logger Pro, the actual software. It showed us that the position time graph looked like this. It showed us the velocity time graph looked like this. And of course, we had to draw the motion map ourselves. So that was scenario one. Here's scenario two. Excuse me. I had the tumble buggy now out in a positive position away from the zero, facing the detector, traveling with a constant velocity back toward the detector. So, pause the video. I want you to try to sketch what you think that looks like, what that should look like here. Okay? Do that, pause it, and then come back and I'll show you. So, what we have here is a line that looked like this. The line started with a positive position away from the zero. That's the tumble buggy over here, way over to the right on the positive side of zero, way up here on our graph. Moving toward the zero position. Again, getting closer and closer and closer to the t-axis or the zero position. That's what the buggy did. Oh my gosh, we should have done the motion map first. So motion map, that means it started way out here, the buggy did, moving this way toward the origin, and in fact got just about all the way to the origin as we see on the line on the graph. So that would be the buggy starting with a positive position, traveling in the negative direction toward the zero position, which is what we see here, which is what this is telling us. Now we have to look at the velocity time graph and think, okay, where do I put my line on the velocity time graph? Remembering that the t-axis is zero, all the values above that are positive velocities, and all the values below that are negative velocities. How would you describe the velocity of the buggy? Well, you describe it like you describe the slope. What is the slope here? It's negative, right? And is it a steady steepness? Yeah, so it's negative and it's constant. Negative, constant. What does negative constant velocity look like over here? Again, that's the question. I would say like that. It looks like the last one we did, only instead of it being up here in the positive, now it's down here in the negative. It's below the t-axis, below the zero, in the negative portion, and it's not getting bigger or smaller. It's staying the same the whole time. Hope that's making some sense. And then lastly, we looked at this one. We said, hey, now I got a tumble buggy. It's sitting out here in a positive position, and it's not moving at all. It is at rest, we would call it. So how do you sketch all of this stuff for a tumble buggy that's not moving at all? So pause the video, sketch all of this in your comp book, and then come back and watch what I say. Well, the motion map would look like this because it is in a positive position away from the zero, and it's not going anywhere. Dots with no arrows. And again, we put them vertically so that we can say, hey, it was doing this for a period of time, and it wasn't moving the whole time. Position time graph. Now, is there any velocity here? No, which means if there's no velocity, we can't have a what? Slope to our line. No slope. Does the buggy have a position? Yeah, a positive position. Where's that? Well, it's up here. Positive position is like up here somewhere. And the position doesn't change. Well, if the position doesn't change, then what does that line look like? It doesn't get closer to zero. It doesn't get further away from zero. It stays at the same place the whole time. Got that? That is zero slope, no velocity. Not going away from zero, not going towards zero. Now, how much slope does this have? Zero slope. Well, then how much velocity is there? Well, if the slope of the position time graph is zero, then we don't have any velocity. Well, where's zero velocity on this graph? On the t-axis. So it has to be here on the actual t-axis, a zero velocity. So it's constant, it's constantly zero. It's not positive, nor is it negative, it's zero itself. So we looked at these three scenarios, and then I assigned, it's actually a worksheet 2 and 3 combined. But I'm going to break it down into parts and pieces, okay? So you're only going to do page 1 for now. So it's worksheet 2, page 1. You'll do all that in your comp book. You don't have to rewrite everything that's there. But it will be scenarios like this, where instead of me showing you a picture of a buggy and what it's doing, it's going to be a description, a written description of something that's happening. You will then have to sketch a motion map, a position time graph, and a velocity time graph for, or to match, what the description of the motion is. So you will put that in your comp book, and of course you'll take a picture of that and upload that for the next class. So Hopefully, I didn't confuse you and this is still making some sense. Again, this is the only thing that we're adding right now. We're only adding the VT graph that we didn't already have before. Okay? So, until next time, take care of yourselves and we'll see you.